Hello and welcome to the 3D printed plastic filament shredder project. Allow us to introduce ourselves.
Hello, my name is Nicholas Petrov, team lead and mechanical engineer.
Hi, I'm Zach Gutalson, I'm a mechanical engineer and the procurement lead.
Hi, I'm Thomas Lewis. I'm the electrical lead.
My name is Jake Chaska, and I'm a mechanical engineer for the team.
I'm Allison Texley, and I'm a mechanical engineer on the project.
Hello, my name is Christian Pavlovich. I'm the systems engineer of the team.
Now that you've met the team, let us tell you a little bit about our project.
Are you tired of having a buildup of 3D printed waste? Well, the EDC was tired of this too, so they have tasked us with designing and building a filament shredder.
Let's take you back to the very beginning.
We were first tasked with building our 3D printer filament shredder back in January of this year. The Engineering Design Center has over 30 3D printers printing daily. All of these printers produced waste in the form of support material, failed prints, and prints that have poor design tolerances. The Engineering Design Center alone produces over 50 kilograms of waste per semester. Our goal for this project is to reduce the volume of that waste to make it easier to transport, so we can move it up to our friends at Precious Plastics up in Phoenix. What Precious Plastics does is they will mold the waste into extrusions to create outdoor furniture, trash cans, and things of that nature. And you might be asking yourself, why not just buy a shredder? The problem is that the shredders currently existing on the market are either too large, expensive, and power hungry, or too small for the EDC's uses. We have industrial machines like the ones that Precious Plastics would use, but those are too expensive and require more than 240 volts that you would typically see at the Engineering Design Center. There's also smaller shredders, but those are designed for at-home use for people who only have one or two 3D printers. So we are targeting the market of maker spaces and other engineering design centers that produce a sizable amount of filament, but not enough to justify the cost of a large industrial shredder. The benefit of this too is that we will be uploading our design and our files for open source under the MIT license so that other maker spaces can use the shredder that we designed.
We researched shredders on the market and narrowed it down to 3 design choices. The Trade City revealed the highest ranking for a single-bladed design. We 3D printed our CAD model and verified that the pieces all fit together. From there, we used a laser cutter to make a wood model where we could then do torque and fitment testing. After verifying our system, we ordered our metal blades and continued testing. We realized the single-bladed design required a push rod in order to get the filament pieces to actually go into the shredder. We decided to pivot to a double-bladed design to mitigate this issue. We 3D printed a small double-bladed design and quickly decided to move forward in the process. We then ordered all of our metal components for the shredder, which then allowed us to conduct the testing necessary to order electrical parts.
To power our double-bladed design, we ended up ordering a 3-phase half-horsepower motor. Along with that, we ordered other electrical components, including circuit protection and our motor controller. Our motor controller is a variable frequency drive, or a VFD. We chose a VFD because we're able to control it using digital inputs from a microcontroller, such as an Arduino, or in our case, we're using an STM32. We went with an STM32 as they are common in industrial control systems. They offer more digital input and output pins, and they are temperature tolerant. Here we are demonstrating controlling the direction of our motor, either forward or reverse, using digital input pins on our STM32. We run the drive and we can see that it reaches a maximum output frequency of 60 Hertz. And then when we send a stop command, it comes back down to 0 Hertz. We change the direction, and then once again, we reach our maximum output frequency of 60 Hertz. And then this is an external fault. This is triggered when the drive is running and our lid safety switch is opened. This requires a reset, and then nominal operation can be achieved once more.
On some of the senior design workshop days, our team spent time at the Engineering Design Center preparing T-slots for further assembly of our enclosure, as well as doing minor electrical testing like connecting our VFD to our motor.
Our shredder successfully meets our interface and environmental requirements. The safe max current for a standard outlet, such as the ones found at the EDC, are 12 amps. Our shredder reaches a maximum of 7.83 and idles at around 2 amps, being well under our requirement. Our VFD is accessed through a user interface, and if needed, the side panels can be removed to access the blades for maintenance. Our shredder also meets the OSHA standard for sound. We met with Maggie Murphy from the U of A Safety Department to verify our sound levels. Results showed that over a 45-minute period, our shredder would output 76.1 decibels of sound, and over a 240-minute period, the user would experience 83.4 decibels of sound before needing hearing protection. An employee would not be shredding for longer than this, and if they were to, the EDC has hearing protection readily available. Through inspection, we found our shredder to measure exactly 26 by 26 inches. Our shredder comes in right at 145 pounds, which is 5 pounds under our requirement. And the shredder accepts 9 by 7 by 6, providing more than enough room for multiple prints to be shredded at a time. We tested the limits of our shredder to find that our shredder surpassed the various requirements, including shred size values up to 75% reduction of its original size, which is 25% above the required value. Our shredder is designed for 20% infill, 3-walled fill prints, but we found that it can shred up to 100% infill with 5+ walls. Lastly, our shredder meets all of our safety requirements. The e-stop cuts off power to the motor when pressed. The shredder will also stop when the lid is opened. The VFD measures current and has a hard stop at 120% its max value to stop the shredding for current values that are not associated with polylactic acid. The blades are enclosed and not accessible during operation of the shredder.
The outline given to us by the Engineering Design Center was to develop a shredder able to process PLA waste with safety measures to protect the EDC employees, to reduce the volume of waste by 50%, to be able to shred automatically, and a shredder operational by December 2025 with all related documentation, designs, and prototypes. As per the lessons learned, we learned that it is important to be aware of manufacturing tolerancing, verifying orders before purchase, prototyping early and often, and also taking videos and photos of your project during the semester.
This project would not be possible without some help, so we'd like to give some thank yous. First is our mentor, Bert Schneider. We'd also like to thank Matthew Briggs at the Engineering Design Center for sponsoring our project. We'd like to thank Maggie at the U of A Safety Department for doing sound testing with us. And we'd like to thank Tyler Elgin with Precious Plastics for meeting with us and giving us insight to the shredder market.
Warning. Team 2550 is responsible for any injury due to negligence and purposes of running safety systems as safety signage posted on the exterior of the product is approved by the U of A Safety Department.